Oh, phew. Okay. All right. Uh, Maisha, aka Misha, depending on who you are, is totally here. So we can totally start. Oh, wait. I mean, Nicholas is here, so we can totally start. I mean, okay, wait. I think we better start. Well, I mean, obviously, like the party, well, the hosts are here. So the part, okay. And also, wait, everything's all messed up. Sorry. Okay. Yes, people are here. People are very here. Okay. I don't even, in this class is so video friendly. I don't even know whether to say hello in the order of the chat or the videos. It's like, okay, but hello, Maisha. Hola, tal, Nicholas. Oh, wait, oh, look at that. Wait, people are still coming. Okay. Hello and good afternoon, Jessica. Hi, Alona. Good afternoon, Jaylin. Hello and good morning in some time zones, Thea. Um, Afternoon, Rachel and everyone. Good afternoon. You see, oh, Rachel's leaving it open. Like, is it a good afternoon? Is it a bad afternoon? We don't know. Is it a morning? We turn to Althea to find that out. Okay, Andrew, good afternoon, and everyone. Hi, Michaela. Good afternoon, Starnisha. Good afternoon, Manoj. Hello, Kazi. Good afternoon, Zimin. Hello, everyone. Oh, so Maisha's like totally okay, bringing it around. Yes, good afternoon, Wishi. Oh, now here's where it gets weird. This is where it gets weird. Oh, Nick, hello, Nick. Oh, no problem, Athea. I mean, hey, you get 11 points for being wrong about something, actually. That's 11 points for Athea right there. I mean, is that girl getting an A or what? Yes, okay. And I get 1 point for being able to call someone wrong. Hey, Leslie. Hi, Maisha. Hi, good afternoon, Elizabeth and everyone. Hello, Ruby. Good afternoon, Catherine. Hi, Athea. Oh, this is where it gets weird. It always gets weird at some point here. Good afternoon, Eric. Your class, you're the first class that has figured out that actually, if you just keep this going in the chat, you could keep me from teaching for the entire period. If you, well, I guess you've done that already. Yes. Okay. Can't start without that. Okay. Hi, Jessica. Absolutely right. I just, Athea, I think you also woke up from a prior life, like 2 lives ago. But yes. Okay. Actually, okay. Anyway, good afternoon, Lisa. Say, oh, gotcha. Right. Hi, okay. This is what. Wait, there's a fire. Okay, I'm not gonna get involved in the fire. But if you were napping on the subway, that would raise assignment 3. So I hope you wrong. Oh, Kazi, right. Sorry, my bad. Yes. Okay. Or well, you're thank you. Yes, see you at 4:30. Right. And that's true for everybody. I'm sorry. If you are here, this is that weird week. If you're here for Physics 102, I apologize. I'll see you at 4:30. If you're for Physics 102, I mean, I sent out a thing, but it's totally understood. It's all confusing. If you're here for 102, I apologize. I'll see you at 4:30. Good afternoon, Mark. Who's multilingual? I don't even. Okay. It's all yes, Mark. Well done. It almost brought us back to physics. This is funny. I'm actually gonna. This is a challenge. Like, if you guys can keep the chat literally going infinitely for an entire class, like add to the chat faster than I could come up with, and thereby keep me off topic for an entire class, that would be an achievement. That's almost beyond 100K. So, and anyway, whatever. Okay, yes, was watching it. I think that's what you're doing right now. 48. That is what you guys are doing. You're literally trying to keep me from teaching by keeping the chat going that fast. Oh my God, I'm literally worried that someone's got like a TikTok in the chat. That's what's about to happen, isn't it? You guys have an algorithm, a social algorithm for everything, don't you? I'm literally scared. I'm looking at, I see there's 47 messages in the chat. I don't, and the problem is, it's really clever on your part, as everything is with this group, because literally I could just say, I'm going to ignore the chat. I'm going to teach. But the thing is, all it would take is one legitimate physics question. Like, all it takes is one person who has a legitimate physics concern and all that chat. And I have to find out. So I have to look at the chat to find out. So like, I'm totally at your mercy. Oh my God, I figured you out. No, you figured me out. Oh my God. No, I'm like literally, I might have to leave this class to go ask my wife what to do. Or maybe I'll ask on YouTube what to do. Wait, okay, no, all right, I'm gonna scroll, but very fun. Oh my God, this is funny. Well, I do want to teach actually, especially since someone pointed out, I think it was Starnisha pointed out that like I might not even see you all next week. You better let me teach today. Oh, and I'm gonna say this too. Oh, here I'm gonna pull a power. This is such a rude thing. For the record, and I'm kind of, this is not a joke. I'm going to go back to the chat because just in case someone doesn't have a physics thing, and I do want to teach. But Starnisha's question from Monday, just for the record, there 3 weeks from today. I mean, I made it official. I spoke to Professor Walters, who also teaches a section of this class. We spoke at midnight 2 nights ago or whatever. So 3 weeks from today. I mean, don't get all crazy about this, but just so you can mark your calendars. Well, we can still make it subject to your input. I'm not going to make it subject to your input right now because your input is scaring me right now, but you can pretty much start banking on that 3 weeks from today, we will post an exam that you'll then have all weekend to do and return like for Monday of the following week. And we'll talk about it and all that, and don't get all like crazy. But what day is today? Today's October. Today's the 6th, right? So it's October 27th that I'm talking about. I mean, that does involve Halloween, I'm sorry to say. But anyway, you can mark your calendars on that. We'll talk more about that later. Again, you'll have a practice test. We'll have plenty of ways to prepare for it. It won't sneak up on you. But yeah, 3 weeks from today is when we'll post it, and then it'll be due on Monday. But anyway, okay. But that's like a shout out to Starnisha's question. And okay, okay. And I'm reading the chat. I may not make a joke about every joke because I would like to sort of try to teach. And I will tell you this too, in the class this morning, I actually did get ahead of the game for a change. We actually started going through and getting answers for homework 4, even though homework 4 is not even due till Monday. So check it, check it. Like we're doing a little bit of flip here. I'm actually going to help you with the homework before you have to do it. Weird. But that's only if I get to actually teach. So not that that's some students are doing. It's not us. It doesn't matter. Whoa, Leslie's thing is like scary. Whoa. By the way, oh my God, I'm going to ask my. Okay, look, legitimate. All right, it's legit, but I mean, it doesn't mean. Okay, and I want you to. Oh my God, I'd be mad if there was a fire and I wasn't there. I think if there's a fire and you're not there, you're mad because like people think you caused it. That's not inappropriate. That was not appropriate. I take that back. Totally inappropriate. Okay, let's physics. But by the way, my brother, my actual like brother, is totally FDNY. I mean, he actually drives the truck for Engine 55 in Little Italy, like for real, which is not near John Jay, obviously, but so he usually does know where the big fires are. I'll ask him about it. Okay, sleep. Yeah. What are you trying to say? Okay. Oh. No, I mean, we talked on the phone at midnight. Why? Because we have no lives. What will be on the exam? I will get to that. There is an exam. Yes, I'm not going to, that's a legitimate question. Nicholas's question about the exam. I just don't want to get like involved in it right now because I want to get back to, but I can tell you this right now, the topics that are on the exam, the topic is kinematics, like i.e. the stuff that we're doing right now. There won't be stuff on the exam that you won't have seen before the exam. It's not like from the textbook. It's just like from what we do in class, but it's kinematics, like displacement, velocity, acceleration, which is what we have to get into now, constant acceleration, but you'll see. Okay. We could totally have a Halloween theme class. Do you know, okay, I was literally dressed in a Halloween costume. I was dressed as I can't even remember what's it called, the March Hare from Alice in Wonderland. You know that, like there's the White Rabbit, but then there's the March Hare. Like the March Hare is like one of the characters at the Tea Party, right? I was dressed as the March Hare on one day at John Jay, like teaching at John Jay, like years and years ago, on the day of Halloween. You know, it was like a weekday. So I was dressed up in a completely ridiculous costume. I was dressed up. I was teaching. And then my department chair called me into his office in the middle of the day for a meeting like that was not scheduled, wanted to talk to me, and he was very scary to me. I was always scared of him. And I was certainly scared if we had a spontaneous meeting that I didn't know about. I was called into his office. I walked into his office dressed as the March Hare, like mortified, thinking I'm about to get in trouble for like dressing up or whatever. And then that's the day he told me that I had gotten tenure. I didn't even realize it. And I'm sitting there in a costume. It was ridiculous. Okay. Okay. No, we weren't meeting with Sheehan. I mean, well, Sheehan's very responsible. He totally responds to, I mean, dude, I mean, Sheehan would probably respond if he knew there was a fire. Okay. Yes. Direct chat person about having to leave. Yeah, it's definitely okay if you have to leave because we're obviously not doing anything. No, yes, totally. Thank you for asking. Okay. Yes. Oh, see, she's question is what just legitimized all this other stuff. Not that a fire isn't legitimate. Some of my best friends are fired. But she's question, yes, the whole point of the 5-step method of problem solving that you're practicing in the homework and everything is that's practicing for doing in the exam. Like the exam is like one big homework assignment, basically. And yes, so yes, good question, Wishi. Okay. Final exam. Okay. Yeah. Oh my God, 99. Oh wait, you are doing this. Okay, 99 Mr. Now you are being mean. All right, I'm gonna walk away from the chat for a minute. I'm going to take the gun and leave the cannoli, so to speak. I'm gonna put down the weapon. I'm gonna put down the chat for a second and just start teaching just to see what it feels like. Okay, I will go back to the chat, but it is hilarious. I mean, you totally get credit that you have 99K new message subscribers in the chat. Like, yes, good for you. And yes, it could be done. You could keep me from teaching the whole time. But also, and the thing is, I probably almost would do, but there is this exam coming up, and there are 2 other sections of this class that aren't clever in the same way that you are. And the exam will be written, by both professors for all 3 sections. So I wouldn't want to put you at a disadvantage. I wouldn't want you not to have material that prepared you for the exam. So I'm going to put the chat to a side for a second, or at least I'm going to make this mature step and go like this. I'm going to switch. Okay, here's where we're going. So the board has just changed. Okay, I'm going to change that. No. But you guys are hilarious. By the way, I'll also say this. This is a serious, but with all these jokes about like, is everybody getting an A or not, or maybe it's not a joke. I don't know. I actually think a lot we're going to get A's in this class. Whatever. Administrator enter the waiting room. Now you're scaring me. Okay, someone named administrator. Someone's about to give me tenure again. Or approve. Someone probably thinks I'm still dressed in a Halloween costume, actually. But don't hesitate about asking me for recommendations. That's my serious one plug for the moment. Okay, I mean, like you obviously are a very dynamic, very cool, memorable group, and I do want to make it clear that when it comes time for you to apply to graduate schools or summer job or job, like I'd be happy to help with that process. And that's real. Just so remember that. And you have my texting information to initiate that process if you want. All right, I'm going to ignore the chat for at least a moment. And if anybody does have a legitimate question about physics or like the examiner saying, I might encourage you to actually use your voice and shout it out right now, because I am too tempted by the chat. I'm a little scared. So I'm going to set aside again. People have commented in public that I have issues with attention deficit. I might or might not deny that. So I have to be very careful here. And I've been unmedicated for years. You can see the result. So I'm putting the chat to the side for the moment. If you have an actual physics question, please. See, I'm even, as I'm saying, I'm putting the chat to the side, I'm like scrolling at it. Like, all right. So we're going to start talking about physics for a moment. Oh my God. Okay. See, I'm seeing the chat, even though I'm trying not to. Yeah, one of those people on YouTube literally did ask me if I was a wizard. And he did not put a smiley emoji after it. And it actually really scared me. Okay. And we're probably going to see that person in Althea's box like tomorrow or something if we're not careful after her nap, but before the fire that she totally did not at all set because she was nowhere near it, I promise. Okay, now making jokes about fires. People. Okay, here's a story. we're going to get into another equation today, believe it or not. We're actually going to double our list of equations in this class. And we're going to start actually moving forward and making this physics look a little bit more like math, for good or for bad. In order to do that, I am going to summarize one more time what the upshot of the last class was. The upshot will never go away from us for the rest of our physics life. Like, the upshot is this thing called Galileo's principle of relativity. That's the upshot of like the train of thought assignment of yesterday and all that. As John Ford, I believe it was, pointed out, like, this is the same relativity as is ultimately appropriated by Einstein in 1905 and becomes the special theory of relativity. And then later in like 1915 and 1920 becomes the general theory of relativity. It all starts with Galileo's principle of relativity in 1626 or 1632, depending on what book you're talking about. It starts in the mid-17th century with Galileo. It starts with the question of, like, how, it starts with the question of, is the Earth moving or not? On the one hand, I totally do not feel that it is moving at all. I have no reason, in fact, to think that it's moving at all for centuries and centuries and millennia, and minutes and minutes of daily life. Like, let me say that again. For any minute of your regular everyday life, there's literally no motivation or impetus or sensory stimulation to suggest the thought that your ground is hurtling through space at any kind of speed at all, let alone a speed of 65,000 miles an hour. Also, for centuries and millennia of documented, written, careful, thoughtful observations of the sky and of the ground, there was not a heck of a lot of reason to suspect or believe that the Earth was doing anything but sitting still at the center of the universe. But then in the mid-17th century, a bunch of astronomical data started to, in the centuries leading up to the mid-17th century, an accumulation of astronomical data started to suggest the possibility that maybe it might be an easier way to make predictions, a more mathematically clean way to start looking at the universe, if we started to maybe even consider or hypothesize or act as if the Earth might actually be going past the sun rather than the sun going past the Earth. Like, people before Galileo, such as Copernicus, started suggesting that we could explain and account for an increasing accumulation of sort of odd astronomical phenomena, such as the retrograde motion of planets. If we would just even act or suppose or model or hypothesize that the Earth moved through space, then Galileo vastly increased the amount of surprising astronomical data by making his own telescope and looking through it and recording and making really good drawings of what he saw night after night after night. So then Galileo starts really advancing this possibility that it might be worthwhile to regard the Earth as moving. But then, of course, there's a lot of arguments he has to pit himself against, not the least of which argument is, are you crazy? Like, look at your feet, yo. Like, and that is an argument, seriously. Like, look at your feet, look at the ground below them. Look at what happens when you jump up and a wall doesn't slam you in the butt. Does it feel really, like, do you really think we're moving? Says any reasonable and advanced and like intuitive thinker to Galileo, or many. And Galileo says, doesn't say direct, well, he does say directly, but in various different ways and in various different books, Galileo puts forth this principle that we are going to keep returning to over and over again through the course, through the next course. And we're going to keep returning to, just as Galileo did in his writings, we're going to return to it in different forms. Like, there's different ways of saying this principle. Each next form is a slightly more advanced or a more logically sophisticated version of the same idea, but each new form kind of opens up more insight and perspective and ultimately more equations and more problem-solving results, right? I'm just, again, summarizing from yesterday. The principle itself, and this principle is not meant to prove that the sun sits at the center of the universe and the earth necessarily actually moves past it. No, it's not meant to prove that. It's meant to prove that there is no actually about it. Oh, darn it. I just saw in the chat. Okay, I'm going to that out. The principle that we are looking at now, Galileo's principle of relativity, is ultimately a principle that is meant to show us how it could be that we could be confused about that the earth could in fact possibly be moving if we don't feel it. It doesn't prove that the earth is moving or is not moving. What it proves is that there's not only one way to look at it. The principle that we said yesterday says that the laws of physics, oh my God, you guys are still going in that chat and you're totally not talking about physics, just for the record. Not that I am looking. The principle says, and form number one, sort of the most original or classic version of the principle, and it was written down yesterday. I don't have it written down here today, but the principle says the laws of physics, whatever they are, whatever they're going to be, the laws of physics are, and put another way, let's say the laws of motion, whatever they're going to be, they're not going to change from one motion to the next, because that would make no sense. That's not a physics discovery, by the way. Let's just get this straight, right? The principle comes before laws. That's why it's called a principle. The principle, oh, is there a volume issue? Well, not that I'm looking. Tell me if there's actually a volume issue, but okay. Oh, I actually saw I see a little physics in the chat. The Galileo did use the idea of a ship, yes, and I want to go back to that. Okay, good. And I'm sorry, I did miss a lot of the chat in the middle, and if there is physics in there, I do apologize. I mean, even if there's good jokes, I apologize. But and yeah, Galileo did use the idea of a ship in one of his great writings called the Dialogue on Two Chief Systems of the World. Yes, he did discuss a ship, and we will go back to that discussion. We will. But the original principle says, the original principle doesn't assume anything particular about physics laws. It doesn't actually assume anything particular about physics. It begins to tell us what kind of assumptions we can make in physics. The only thing the original principle really assumes is something about the word laws. It's saying whatever the laws of motion are going to have to be, they couldn't possibly differ from one constant motion to the next, because then they wouldn't be laws of motion. They would be circumstances or individual instances or cases, right? Like, again, a law about what cars are supposed to do at a traffic light does not differ from car to car or traffic light to traffic light. If it did, it wouldn't be a law. That would just be a circumstance. So Galileo says, almost self-evidently, I mean, or we're meant to take it, he says, whatever the laws are going to be, they're not going to change from one constant velocity to the next. Like, as long as you're going at a certain unchanging speed in a certain unchanging direction, whatever that speed is, whatever that direction is, the laws can't possibly affect you in some way that's different. Okay, that's funny. That's funny. There's no way that the laws could affect you differently from the way they affect somebody else at some other constant speed and constant direction, right? Okay, that's the principle in its first form, in its most pure form. And again, if you're almost tuning out or like dealing with the chat because it almost seems like completely obvious and stupid, like why does that even have to be said? Then good, because that means at least you think it's true, right? But here's why it has to be said, because then, again, I'm just summarizing from yesterday to try to catch us up to today. Let's try to bring this in. But if form number one is the laws are the same at all constant velocities, then form number two says, then form number two says, well, if that's the case, then any experiment you'd ever do at one constant speed or direction will have to work out to the same result. I mean, if you do any experiment at one while you're in a vessel going one speed in one direction, then whatever experiment you do is going to have to work out and produce the exact same result, the same outcome, the same data as if you did it at some other constant speed and direction, right? It's just a subtle shift. Notice from form number one to form number two. Form number one is almost maybe self-evidently obvious that it almost seems like it doesn't have any content. It almost just seems like it's like the definition of law. But then we just like push it slightly into form number two and say, okay, if the laws are always the same at all speeds, then experiments will always result the same in all speeds, right? Again, and again, this doesn't assume any particular experiment. It doesn't assume that we have all the technology in the world or no technology. And it doesn't even assume that we know all the laws. It's just saying whatever experiment you sort of can imagine doing with whatever laws you do know, if experiment means like isolate variables, collect data, and reproduce, well, then again, I'm just going to always go to the simplest thing. Just imagine that the experiment is dropping something, just dropping something from my hand. I believe that we all know, even if we haven't written down all the. Okay. Also remember that the way the chat works, guys, so the fragments come in and I see a fragment of the chat and then I kind of know whether it's about physics or not or whatever, but I don't see the whole thing. So you are continually tickling my fancy. So I just saw a now that you are, but I don't know what the rest is and I'm not going there. So just so you know, that's what's again, let's assume for a minute, the hypothetical that I have ADHD. If any of you in the room also have it and know what it's you realize you are setting my brain on you're putting, I don't even, I'm it's very, you get my point. It's very tricky not dealing with the chat right now. I don't know which is harder, dealing with the chat or not dealing with the chat, but okay. Oh my God. Okay. I'm totally not looking. Okay. The point is, if I drop something and I'm standing still if I'm just sitting around in my living room at speed 0 and I drop something, I think it's pretty fair to expect that the thing I drop will land directly below my hand. That's an experiment. I can do the experiment or I can picture the experiment. I don't think I'm going to be surprised either way. If I'm sitting around in a stationary room, and I am not even going there. If I drop something while I'm sitting around in a stationary room, and if I call that my experiment, I expect the object to land directly below my hand, right? That would be the result of the experiment. Drop something, it will land, it will fall in a straight vertical line and land directly below your hand. That's my experiment. But if I take form number 1 seriously, then it leads me to the form number 2 conclusion, which is, well, then even if I'm going 100 miles an hour or 500 miles an hour, even if I'm in an airplane and I drop something, I would still expect it to land directly below my hand because the laws are the same, whether I'm in an airplane going 500 miles an hour or even on an airplane, whatever. If I'm going 500 miles an hour or 0 miles an hour, well, now that looked like physics, what Nicholas just put there. I would argue ultimately that okay, wait, so this may be important. And also I am trying to be realistic. I have to be careful realistic. That is, I have to make sure there aren't a lot of other circumstances or other variables affecting what I'm picturing or affecting what I'm doing. In fact, this is the contribution of Galileo, right? Remember what we mean, people have been thinking about physics for centuries, whether they called it physics or not. And people have been making observations. People have been getting data in one form or another through their senses from the world for centuries. The thing that Galileo shifts, and you know this from your other classes and stuff, but the thing that Galileo shifts is that he comes up with a scientific method for collecting data, and an intrinsic component of this method is that Galileo comes up with a way, or it comes up with the idea that it's super important to control your data collection procedure, control your variables, right? The whole idea of the scientific method anyway is separation of variables. The whole idea is that we control our procedure enough so that whatever one variable we're trying to study, whatever one input we're trying to change, and thereby see what the resulting output is the only input that we're changing. This is the difference between the scientific method and this is the difference between experiment and just observation. The difference is that Galileo when I do an experiment or consider one, I do my best to hold everything constant except for the one variable that I'm trying to tweak, right? So why am I saying this right now? To go back to what I think Nicholas put in the chat, that I think No, what I think Nicholas brought up like a legitimate like concern, like what I'm saying is if you're in an airplane or say an elevator, whichever is easier to picture, or like a really good subway train, like a subway train in Tokyo or something, but really like an airplane, if you're in an airplane, and I'm not talking about when the airplane lifts off, and I'm not talking about when the airplane lands, and I'm not talking about when the airplane turns or hits turbulence. In other words, I'm talking about a section of the flight. And I'm not trying to be weird. I'm not saying I'm only talking about perfect conditions. No, I'm just saying this. I'm talking about once you're in the airplane. I'm talking about when you're in the airplane going at a constant velocity, when your speed and your direction are not changing. And that's not, that is a controlled situation, but it's not an idealistic or like fantasy situation. It's not Smurf Village. I mean, we've all, if we've been in an airplane at all, we've been in an airplane and experienced that portion of the flight where you're cruising, right? They literally call it cruising because like you literally are. And they say at that point, that's when they say the captain, okay, we've achieved cruising velocity and cruising altitude or whatever. And the captain has said it is safe for you to unfasten your seatbelts and move freely about the cabin, i.e. smoke them if you got them or whatever, right? And that is like literally they are saying it is now safe for you to walk around this freaking like metal box that's 5,000 feet above the ground and going 500 miles an hour through the air. They're saying it's safe for you to freaking walk around and start complaining about the movie or passing martinis to your neighbor and using the bathroom, for heaven's sake, right? And they're saying that, and it's true, and you do it. Like you get up, you walk around, and maybe you take a nap, or maybe like someone says, can you pass me the cocktail peanuts? And you don't go like this. Here you go, here you go, here you go, right? Like you just go like, here. Like you act like you're in a hotel room. And if you jump up, you don't worry about the back of the plane slamming you in the ass, right? When the plane is cruising. Like, so I'm trying to make a point here, and it is on point, but I'm also sort of trying to respond to Nicholas's question. Like this doesn't happen when the airplane's taking off. No, for sure. That's a jostly, mossly situation where you're feeling something's going on. And that's what I want to ultimately get to in this lecture. I mean, that is acceleration. That's where we're going with this discussion. But what I'm saying right now is as long as you're not accelerating, as long as you have velocity that is constant, if you have velocity that's constant, then any experiment you do, whether it's a simple experiment like drop something or a simple experiment like hand somebody peanuts, it works out the same way as it would if you were just sitting in a hotel room because the laws are the same as what they would be if you were in a hotel room. Like this is the principle, right? So therefore though, and that's why you can act all normal. Oh, cool. Okay, I'm going to actually assume that that's like a serious, cool. And that actually gets points for closing the conversation. No, because I mean, and I'm upset because again, I mean, the chat thing is weird, but I really think what Nicholas brought up before was like a legitimate concern, and it seems like maybe we are resolving it. So cool. But like the fact that you even trust airplanes at all and can get all sort of normal in your feeling in them is a very deep thing, right? I mean, it means that you're like legitimately confused. Like even when you think you're not confused and you're like, no, I've worked it out. Like the airplane is moving, like, okay, we're moving. There's nothing about your actions that suggests that you think that the airplane's moving, right? You can totally treat it like it's not, even though in one side of your mouth, you say the airplane's moving. Just like on Earth, like we walk around building solar system projects in third grade saying, we believe that the Earth is going around the sun, but there's nothing in our conduct that in any way seems to subscribe to that belief. Yes. Oh, very good. Very good. And again, I'm being weird with the chat. Like I'm sort of seeing it. I'm sort of not, but all of it, what I'm saying right now, that's really good, Ruby. That's really good. That's definitely points too. Wait. Well, planes trust you very deeply, I think. No. And look, and I'm not, this is not a plug for that you should always feel safe in an airplane. I'm totally not saying that. But I am saying the fact that we ever feel safe in an airplane, or that somebody thinks we should, or not even feel safe, but just act normal, or forget airplanes, in an elevator, right? Like there's a period during an elevator's ascent where you can literally forget or not know whether like it's doing its thing or not until the doors open and you find out, right? And to Ruby's point, what I'm saying right now, what I'm saying is this is not just confusion just because like we're dumb or weird or stoned or something like that. This actually is the confusing but very deep and ultimately resolvable character of velocity. Okay, I am gonna actually pause and look at the chat in a second because I feel like some legitimate things are happening in the chat. But look, seriously, what I'm trying to say, and hopefully this is a little bit of fun, but I'm saying if ever in your life you've ever been confused, even for a moment, about whether you're moving or not, I don't care if you were under the influence of sleep deprivation or narcotics or whatever, like all these things that there could be 1,000 reasons that you might be confused, that your senses might be confused for a minute about whether you're actually moving or not. But once your brain resolves that confusion and then moves on, what I want to say is, hang on, that confusion told you just as much about the world. The fact that you could have that confusion tells you something very important about the world. And even if you think you resolved it for a minute, the truth is your resolution was probably more primitive, less correct, less sophisticated than the confusion itself. The minute you and all of what I'm trying to discuss right now is called Galileo's principle of relativity, but Ruby is absolutely right, and we will see in this course that it then becomes Newton's first law of motion. I mean, it's a great insight on Ruby's part. In fact, in this arguably Newton's first law of motion, if you've heard of it, and many of you have in other contexts, and we're going to study it, but Newton's first law of motion is merely form number 5 of Galileo's principle. So at least Ruby is, I mean, more than Ruby, lots of you are seeing what's happening here. But I'm saying Galileo's principle starts off as just a statement that, like, all the laws are the same no matter what. That's the principle. But if we keep pushing and pushing and pushing the principle, and as of yesterday, we got to form number 3, soon there's a form number 4 to come, which is very mathematical looking. And then there's going to be form number 5, which the world ends up calling Newton's first law of motion. Like, so if Ruby or anybody else is seeing the connection between what I'm saying and what you've heard of as Newton's, that's absolutely great. It means you are getting what I'm saying. And what I'm saying is this, and I will look at the chat. I will. Let's see if we're going. What? Yeah, well, there's a little bit of that goes, yeah, I mean, there is something true. I mean, word. But it's okay. Galileo's name still lives on. And the truth of the matter is, in a way, Einstein, that's part of what Einstein did, was give the credit back to I mean, someone put in the chat, I think Nicholas put in the chat, like, Newton took all the credit. A little bit of that, there is some truth to that. But in a way, what Einstein did in 1905 was he made sure the whole world knew that it had come from Galileo in the first place. Like, that is part of Einstein's contribution. But what is the point of Galileo or of Newton or whatever you want to call it? It's that once you say that the laws are the same at every speed, at every constant speed and direction. Oh, and again, not and changing. Like, I'm not saying that you never feel something in an airplane, but once you say that the laws are the same at all constant speeds and directions, so then you get in an airplane that's going at some incredibly high but constant speed and direction. Then if the laws are the same, that means experiments always work out the same, which means if you drop a pen, it will land directly below your hand, just like it would if you were sitting in a parking lot, right? Or if you pass someone the peanuts, you pass them the same way you would in a parking lot. You don't compensate for the speed of the plane when you pass someone the peanuts, right? Blah, blah, blah. Then that's interesting, and that makes us feel safe or maybe even confused in a plane. But then what that also means is that then you actually cannot use any experiment at all, no matter how sophisticated. You can't use an experiment to find out whether you're actually moving or not. So it means that for that moment, you're confused, let's say and I know I said this yesterday, but I feel like more and more people are getting it. And it's really important to get this. It's really important to get that it's not just about getting something and writing it down and memorizing it. What I'm asking you to get is the idea that when all of us thought we got something before, we were wrong. When we thought we got that the earth moves past the sun, like in 3rd grade, like, no, that's not actually the deal. Or when you're sitting there, if you're in an airplane and you're confused for a moment, maybe because you just woke up, and you look out in the sky and you're like, oh, wait, am I moving or not? What's going on? And then you see like some clouds going past you, let's say. So if for a moment you're like, wait, okay, does that mean that I am moving? Because I see clouds like in a blur. So does that mean I'm going forward and the clouds that's why the clouds look like they're blurring back? Like, are the clouds sitting still actually, and I'm moving forward actually? Or are the clouds actually going back and I'm actually sitting still? If you ever ask yourself that question, right? If you ever ask yourself that question, what Galileo is saying is, well, I don't know how you resolve that. But I'll tell you this, if you just resolve that in your own head, if you do some decision in your own head, well, then that's just empty theory. That's, that's your head. I don't know why you think that that means any kind of real truth. But if you want to scientifically resolve this question of whether you're actually moving past the other thing or not. Oh, and I know what I was just going to say. Like, you might think the clouds are a dumb analogy, or you might think the white lights in the subway station are a dumb analogy. Like I'm saying, if you woke up and you saw white lights going like that for a moment, you might not know. Or is it actually the case that I'm sitting still and those white lights are attached to another subway that's rushing past me? Or is it actually the case that those white lights are attached to a subway that's sitting still while I go that way? If you ask yourself that, first of all, you've got to understand that you're asking yourself the same question that anybody and everybody ever ask themselves when they look up and see the stars going past the earth every night. And when they see the sun going past the earth every day, like we know there is relative motion. There's no question about that. There's no question that the earth and the sun are not doing the same thing. There's no question that the earth and the stars are not doing the same thing. There's no question that the airplane and the clouds are not doing the same thing. But if then we stop and say, okay, but which one of them is actually doing the thing? Which one of them is actually sitting still and which one is actually moving? What Galileo says is, well, if you attempt to resolve that with an experiment, good luck, because there isn't an experiment you could possibly even think of. I don't care how much technology advances in 100 years. It's not that we have limited technology. You couldn't even conceive of an experiment that could resolve that question. If you think you could resolve that question by like dropping something and going, oh, it landed below my feet, so I guess I'm sitting still, you're wrong, because it would land below your feet whether or not you were sitting still. The laws are the same at all constant velocities. So Galileo's saying in form number 2, there is no experiment that you could ever do to find out whether you were actually moving through space or not. Like, you can tell that you're moving past that thing, or that thing is moving past you. But as to which one of you is actually moving and at what actual speed, there's no experiment you could do to figure that out. None. Because all experiments will always result in the same result, regardless of what the answer is. Therefore, the experiment will tell you the answer. So then what Galileo says, and I know I'm like going crazy here, but this is so super important. Really, all of physics rests on this. And the more you think about this, and the more, and you can see I'm getting excited, right? To note for the record too, even if you think I'm saying the same bloody thing that I said yesterday, and even if you're thinking that I should move on, or like you're thinking like, I get it, Jesus, I mean, you said it yesterday, Average, but please note, no joke, I say this like 3 times a day, every day for over 26 years now. I've been saying this 3 times a day, every day since 1992 when I started teaching. Okay, like seriously, right? And I'm saying each time I say it, I understand it more and get more excited. I don't get more bored by this. I couldn't fake this. This doesn't get less and less interesting. Every time I say it and think about it, what happens in my brain is my ability to predict the rest of physics, my ability to figure out the rest of the equations on my own, let alone use them, it grows. Every time I say it, I realize all of physics just explodes from this. The more you actually get how it could be that the earth could move at 65,000 miles an hour all the time with us never feeling it, the more you won't just understand how to apply physics equations, you'll understand them, you'll anticipate the equation before it's even put in front of you. You'll be able to invent the rest of physics the more you really contemplate this principle. It is infinitely deep, honestly. And what it says in form number 3 that we were trying to say yesterday, and then I will move on temporarily, but what form number 3 says is, here we go now. If from here on in, as of 1626 or as of 1632, if from here on in we're saying there's all kinds of truths in the world, and there's all kinds of reasons to believe stuff when you're in an argument, there's all kinds of different ways to resolve whether who's right and who's wrong. Like maybe you look at numbers, maybe you look at God, maybe you look at your emotions. There's all kinds of ways. But from here on in, as of 1626, we're going to have a new way that we call science. We're not saying it's the best way. We're not saying it's the only way, but we're saying it is a way. It's called science. And all of you in the room, or who are watching this video, have elected to like major in this thing called science, or try to get a job in this field called science, or try to go to graduate school in this field called science. And if you think that science is a particular, specific, and worthy way of getting at truth, the fulcrum, or the pivot point, that like the rubber meets the road in science at the data collection level. Like what we believe in science is what we can get out of experiment, right? It doesn't mean that's the only way to know truth, but it means it's the scientific way. What is true is what comes from and goes back to experiment, right? That is the judge, the jury, and the executioner in science, certainly in physics, is what the data says reproducibly and methodologically when we collect it with our senses and with instruments of measurement from nature. Experiment is the arbiter of truth there as of Galileo and as of 1626 or 1632. So in form number 3, this is like all slippery, like sneaks up on you kind of thing. So by form number 3, Galileo says, well, if we just establish that whatever the laws are, they're going to be the same no matter what. And if from that we infer that you could never do an experiment to figure out whether you're actually moving or not, right? If you can't do it, because any experiment, like whether you're actually moving or not, the experiment's going to lead to the same result. You drop a pen, it's going to land below your hand, no matter how fast you're going. So you can't drop a pen in order to figure out how fast you're going or whether you're going at all. So then from here on in, if the only way we ever figure out truth or meaning or significance in what now becomes physics or science, if the only way is experiment and there's no experimental way to figure out an actual velocity of a single object, then Galileo says in form number 3, I guess it's a meaningless notion. It's meaningless. What is meaningless? The velocity of a single solitary in and of itself object. Velocity, so I'm repeating this. This is a repetition from yesterday, but the more you actually chew on this, the more you will see everything else in physics. And let me also say again, half of your brain should probably be thinking that you already knew this. Part of every one of you who's listening to this already knew this in a way. But what you didn't know is that it's universally, absolutely 100% and powerfully true. What you kind of knew is that sometimes you knew this. Sometimes when you just accept the idea that the Earth is going at 65,000 miles an hour, your brain is accepting that idea because you kind of know you don't have to feel velocity in order for it to be there. But what I'm saying is it's always true now. It is always true that velocity is not, and so this is what's written on the sheet, velocity is not a property of any single object by itself. Velocity is a relation between one object and another. Velocity is intrinsically relational. It is relative. This is what we mean by the principle of relativity. There's no concept of velocity other than as a relation between two objects. If you ever want to discuss the velocity of one object, you need a second object as a basis of comparison, or as what we call a frame of reference. Literally, we're saying, right? So if the question is, okay, enough nonsense. Like, so what's the deal? Like, is the Earth actually moving or not? The answer is, compared to what? If you want to know what is the actual speed of the Earth, is it actually 0? Or is it actually 65,000 miles an hour? Or is it actually 650,000 miles an hour? The answer is, well, compared to itself, compared to the Earth is a velocity of 0. Compared to the sun, the Earth has a velocity of 65,000 miles an hour. However, at the same time, compared to the Earth, the sun has a velocity of 65,000 miles an hour. We can say that the Earth is sitting still and the sun is moving past it at 65,000 miles an hour. We can equally say the sun is sitting still and the Earth is moving past it at 65,000 miles an hour. We can equally say that the sun is moving past the galactic center at 650,000 miles an hour. And therefore, compared to the galactic center, the Earth is moving at 715,000 miles per hour. Any one of those statements is equally correct, because each one has a different basis of comparison. Literally what we're saying in the end is, if I walk up to ever from here on in physics and I say, so what is the speed of the car? Or if I say, how fast is the car? Actually, you should look at me like I'm insane. or at least insufficient or tricking you. If I say, how fast is the car? In fact, from now on in physics, when we're doing equations and stuff like that, if I write down V as in velocity, meaning car, I shouldn't just leave it at V. For 99% of our cases when we're doing equations and things like that, we're going to put subscripts next to the V. We're going to put two subscripts, one to refer to the V that of the object we're talking about, and another to refer to the object that we're comparing it to, because we can't talk about one without comparing it to the other. Literally from here on in, if I say to you, how fast is the car? You should look at me as though I just asked you, how taller is your sister? Like literally, like it's that stupid of a question. Like, and I hope you see what like literally, if I just walk up to you and I'm like, hey, how taller, or I'll leave your sister out of it. I mean, I don't want to say that. I'll talk about my sister. Okay, or my brother, the fireman. If I'm like, my brother's FDNY, which he is, plug for FDNY. If I say, my brother's a fireman, so therefore, I bet you can guess. Like, you probably don't even need to see a photograph. Like, how taller is my brother? And then you're like, wait, what? How taller is your brother? Okay, that's weird. If you're like, how taller is your brother? And I go, yeah. How taller is my brother? Oh, you can't answer? Here, let me show you a photograph. Here's my brother. Here he is. So now tell me, how taller is my brother? You would presumably be like, okay, stop. You would presumably be like, taller than what? And that's what speed. Oh, question.
Yeah. So if we're by that like statement, then how come we're allowed to have like set speeds for certain things, like the speed of light? Because what is it that we're comparing to, or the speed of sound? Like, what is it that is being compared to?
Oh my God, that is a great question. That is truly a fabulous question. Seriously. Now I'm going to give a couple answers to that, and it totally shows that you're totally paying attention. Number one, which I appreciate. That's a very challenging, awesome question. My short, annoying answer is we're going to talk a lot about that in Physics 204. I mean, assuming you're with, but here's the quick answer to that. Those kinds, and he's absolutely right, ladies and gentlemen. Like what Mark just asked is like, then how can you just come along and say that there's certain things like just have a speed, right? And he's right, we do that. And it's a very challenging question, but I do have an answer to it. I just have to give it a look. Wait, okay, right. Now, he just gave two great examples. Mark just gave two great examples, and I'm glad people are involved in this. This is good. And what John just said, and then someone right after John said kind of the right answer to this. Okay, wait, you guys, wait, stop with the Zeus thing for a second, just because really my brain can't handle it. And also we have what? We have 10 minutes. Okay, but
23 minutes.
Oh, what a nice guy. He actually, thank you. Oh, you're right. Okay. So I'm not, thank you for being honest about that. You're right. And I did think it was 410, not 420. Okay. But it's okay. So I can be a little bit calmer. And I will stop and check out the chat in a second, because like I know you're all working very hard at the chat. But look, Mark's question is fantastic. And there is a concrete answer to it. The thing is, I want to make clear, he gave two good examples of things where we sort of say that there like is a speed of them. One was sound and one was light. Now, one thing I want to say is light is the ultimate punchline of everything. Like the fact is, everything Einstein did, Einstein based everything he did on two postulates, two axioms, like literally the whole special theory of relativity, and frankly, even the general theory of relativity, which are enormous. I mean, heavy duty math, heavy duty groundbreaking experimental results, like all this, but they're all based on two axioms, postulates, things. The first of the two postulates is literally Galileo's principle of relativity. So half of all of Einstein is like already done by Galileo. And the other postulate is that light travels at the speed of c in all inertial reference frames. What I'm saying by that is that Mark and John and other people are certainly right. And if you ever bring up light, you're right to bring up light, because light ultimately is kind of like the exception that proves all rules, or it's like the holy grail. Like everything in physics is ultimately pointing toward trying to understand light. Light is a thing that produces its own set of questions and stuff. Like, in other words, I can't fully answer everything about Mark's question about light right now, because in a way it takes us 2 physics courses to do that. Light, but I can say something. I can certainly say something about sound. Well, right. No, that's right. That's right. Like light is a very mysterious, bizarre, but wonderful thing. However, there's still legitimacy to, I mean, there's tons of legitimacy. There's still something I can answer about Mark's question. And it'll help you even see why I'm stalling on the light part. On the sound example, Mark is right to say, like, well, hold on. If like all speeds are relative, how come people can walk around and say the speed of sound is bleh? And the answer is, and again, I love the question because he couldn't ask that question if he is challenging what I'm saying, but it's great. It shows he's getting exactly what I'm saying, so much so that he's thinking of pretty reasonable, like seeming exceptions to it. People do go around saying the speed of sound as though sound has a speed, regardless of what you're comparing it to, which totally sounds like a contradiction to what I'm saying. Here's the thing. What sound is a wave, like I think John and two other people pointed out in the chat. Sound is a wave. We're going to look deeply at waves in Physics 204, but what for the moment, what it means to be a wave is that there is no one such thing as sound. Like there is no such thing as an atom of sound or a particle of sound or a molecule of sound or something like that. Sound is a wave means, to say that sound is a wave means that sound isn't an object, it's a phenomenon. It's a very particular, it's a collection of lots and lots of generally, let's say, air molecules, could be water molecules, could be nylon molecules. But what a wave involves is a huge collection of little particles that are all moving in a highly, highly organized, patterned, and staggered way. Like, which I know everybody sort of like knows and you can picture, but like in order to have a sound wave, we need a whole bunch of particles that are all essentially going like this, like a wave, like you would do at Yankee Stadium or something like that. That still doesn't mean that this still hasn't fully answered this question yet. But what I'm saying is, in order for sound to go from here to there, a ripple, a wave, a dance, a highly organized set of motions must ripple through a vast collection of small particles. The small, generally with sound, it would be air, okay? But it could be water, it could be, but there has to be something that the sound is going through. You may have even heard like sound doesn't travel through outer space because there is nothing in outer space to be vibrating to create this wave pulse. So now, and we're going to study it in depth in Physics 204, but where I'm going with this is this. When people say sound, what they generally mean is sound going through, when they say the speed of sound, what they're talking about is the speed of sound in air. It's a different speed when it's in water. It's a different speed when it's in wood or nylon or whatever. And when people talk about the speed of sound in air, what they're talking about is how fast the ripple travels compared to the big collection of air molecules that are all vibrating to make this ripple. In other words, when people see the speed of a wave, what they're always intrinsically comparing it, they are making comparison, they're just not saying it. When they say the speed of a sound wave, what they really mean is the speed at which the wave travels compared to the medium, the vast collection of particles through which it propagates. So the speed of sound really means the speed of a sound wave compared to air. And that's so true. It's so true that that's what they actually mean. Like, I'm not lying. Like, it's a great question to get. But what I'm saying is, whenever you hear the speed of something, it's generally of some kind of wave thing. Like, we never hear of the speed of baseballs, or this, you could talk about the maximum speed of a baseball, but like not all baseballs go the same speed, not all cars go the same speed or something. But when someone says the speed of a wave, like sound, what they really mean is the speed at which that wave travels compared to its medium. And that's such a real thing that actually, if you move the medium while this is happening, or you move past the medium, you will observe a different speed of the wave. And that's called a Doppler effect. Like, that's actually why when a car makes a sound that's going to your ears, if the car that made the sound that's going to your ears happens to be moving while it does that, or motorcycle, whatever, or your ears are moving toward it when it does that, you actually hear something different from what you would hear if it were stationary, because the fact of the matter is the speed, when they say the speed of sound, they mean compared to the air through which the sound is traveling. And if that air travels, or you travel past that air, you do get a different number. So, I mean, it's a fantastic question. But what Mark is saying is, how about waves? And what I'm saying is, even waves have a specific speed that they go. But I mean, even waves, when we talk about their specific speed, we're talking about in a comparative, relative sense. But it happens with waves, we mean relative to their medium. Now, then light is like a weird version of that. Even light even follows that, but that gets into weirdness for next semester. But yeah, great question. I'm going to take that to mean that you're actually following what I'm saying. I am going to pause and go to the chat. I really promise. But let me just,
Thank you.
and maybe I'll maybe, oh, sorry, Mark. Oh, does that work?
Thank you.
Oh, thank you. You just closed the conversation. That was 10 points or whatever, 9 points for. Thank you for saying thank you. That makes me feel like a human being. I appreciate it. And thank you for the question. Seriously, great question. And thank you, John, for what you put in the chat about the question. Again, I'm going to look in the chat in a second, even though it's risky. But where all this is going, at least so I can pause, at least even if I don't get to everything I want to say, I want to like transition us into material. Like I do want to move on, right? And I'm sure there are some of you who are like starting to go crazy, thinking like, are we ever going to move on? Now, part of me wants to say in physics never moves past this point. Physics is always probing this point in a way, especially when it gets into all the studies of light, all the intrigue of light and Einstein is all about how do we apply this principle to light? Like, how does it work? But in order to move on in the curriculum for a moment, what I want to say is, if you're getting me that I'm saying velocity is not something that a thing has, velocity is always a comparison between one thing and another, then another way to put what I'm saying, okay, the simplest way to put it is we never feel velocity. It's like, it's that simple. We don't sense velocity. You think you do sometimes, or we think we do sometimes. Like sometimes we get like, oh, I get motion sickness. Oh my God, I totally get sick when I'm in a car that's moving. Like what I'm here to say is no, you don't. Like no one gets motion sickness. If we were to ever get motion sickness, if motion were to make me puke, I'd be puking all the time. I'd be puking like 75,000 miles per hour of like psychedelic chunks all the time. Motion is not something that we ever feel. What we feel, sorry. Yes, thank you. Right, that was totally TMI. But what we feel, what we sense is not motion. What we do sense is changes in motion, okay? And this is why I have to keep saying over and over again, which are called accelerations, okay? That's why the course is going to move on now. We're going to move to acceleration. Acceleration doesn't mean the same thing as speed. Acceleration is, and acceleration doesn't mean the same thing as velocity. Acceleration is change in velocity. And that, yeah, right. Actually, good. Okay, I have to. Yes, I even made that. Yeah, we are going to start accelerating now in the course. We are. I mean, and I'm sure some people are like, well, thank God. And I'll see it. Or other people are like, I'll see it when I believe it. No, they're like, I'll believe it when I see it. But yeah, an acceleration is a change in velocity per time. And that's what we actually can sense or feel. That's what we can get sensory data for. Acceleration is a change in velocity per time. And that brings us finally, and I keep saying I'm going to do this, but I'm going to pause for a second just to make sure that I didn't miss anything in the chat. I'm afraid to do that. Oh God, we have 11, 12 minutes. Yeah. Here's our next equation. We're doubling the list of equations that we have here. If A stands for acceleration, and if the bar over it stands for average, as it did before, and if V stands for velocity, as it did before, and if triple equal sign means equal by definition, then we have a new equation here, and it is that average acceleration equals change in velocity per time. And I can go back to the page if you want me to. But note, we now have two equations. We are going to accelerate. Like, I mean, I know that was a joke, but we are. That's cool. Thank you for telling me. I totally appreciate it. Thank you for telling me, Director. I got you. We are going to start moving faster and faster. And the more we, and partly because the more we really get these fundamental concepts, the more, sorry. Yes, absolutely. Thank you for asking. I guess I am sort of seeing this. Yes, absolutely. It will start speeding up because the more you really get these fundamentals, the more we can all do this on our own. The more we have the principles, the more we can apply them with agility, alacrity, and individuality. But what I'm saying now in our second equation is I want you all to see that our second equation is perfectly parallel, and tell me when I can move back. Our second equation is totally parallel in structure to our first equation. It's not a coincidence. And first and foremost, it's parallel in that it's also a definition. It's not a discovery that we made in the lab, and it can never be undiscovered. It's just we're introducing a new term in English, saying that it's shorthand for a bunch of other terms in English, and then giving like letter symbols. Okay, cool. Thank you very much. Awesome. So our two big equations that we have now, which do have a lot of information in them, like, they're just about establishment of meaning of terms, but the meaning is like very deep. But we have that average velocity equal change in position per time, or average velocity equals displacement per time, average acceleration equals change in velocity per time. And notice, I don't know if you can see like all my red markings and stuff, but please notice it's really a parallel structure in that on the left-hand side, you have an average like over some interval or segment or region of time and space, like the average velocity over some trip, or the average acceleration over some trip is what we're defining on the left side. And then on the right side, we're defining it in terms of points, like the average velocity between any 2 points in space and time is equal to the change from one point in space to another, a change in position, which we call displacement, right? Change from one point space to another as the clock changes from one point in time to another, right? That's what's on the right-hand side. So average velocity is equal to change from one position, one point in space to another point in space over point in time to another point in time. Same thing now, average acceleration is going to be defined as change in the velocity at one point in time to another, to a velocity at another point in time, all per a change from one point in time to another. Okay, so it's the same structure, same idea. Yet, well, velocity is displacement over time, and displacement is change in position, if that makes sense. Good question in the chat. I didn't even see who that was, but administrator. I don't even want to know who administrator is, but yeah. Like velocity is equal to displacement per time, or excuse me, average velocity is equal to displacement per time. Displacement is equal to change in position per time, if that makes sense. And so notice here, and maybe I'm not going to, we actually are, okay, we have 8 minutes. What I want you to notice here is that acceleration is a vector. Just like velocity, just like displacement was a vector, displacement specifically means change from one position to another and takes into account positive or negative signs, takes into account direction, displacement does. Then velocity was displacement per time. So velocity took into account direction. It could be positive or negative. If you're going one way, that's positive velocity. If you're going the other way, that's a negative velocity. Well, same thing, acceleration is change. It's not change in speed per time. It's change in velocity per time is what acceleration is. So acceleration is also a vector quantity. Accelerations have direction. And if we're talking about in one dimension of space, accelerations can be positive or negative. I'm actually going to go, okay, I'm sort of breaking I'm going to go to the next page. I'm going to keep going because I would like to help with your homework before you have to do it for Monday. So I'm going to continue to ignore the chat. Please forgive. I'm going to the next page. Notice this very quickly. Just notice, I'm saying acceleration is a vector quantity. That means, first of all, you'll have a non-zero acceleration. So acceleration doesn't just mean speed up in physics. It means any kind of change in velocity. And velocity is a speed and direction. So acceleration is any kind of change in speed or direction. So that means we have a non-zero acceleration if we either speed up or slow down or turn. Any one of those cases is called an acceleration. It might be called a positive, it might be called a negative, but any one of those cases is called an acceleration. And the reason they're all called accelerations, they all have something in common, which is that you feel them. You feel it when you speed up, you feel it when you slow down, you feel it when you turn. Okay, and therefore bump or lurch, those are all versions. Like a bump or a lurch or turbulence is some kind of quick speed up or slow down or turn or combination thereof, right? Okay, so this is, again, acceleration is a vector quantity. Even if you change the direction of travel, that's an acceleration and you'll feel it. Number two, notice, and I have to say that I'm looking at the time. Okay. Number two, there's a such thing as negative acceleration then, right? Accelerations can be positive or negative. And all this assumes that we would first like choose a coordinate system where in one dimension we would say like, okay, that direction is positive for example, we would just choose it and that direction is negative. From now on, I make all my decisions consistent with anything going that way, I'm going to call positive. Anything going that way, I'm going to call negative. Why do we get to choose at the beginning? And furthermore, why do we have to choose? Because velocity is relative, because there is no one, because nothing is objectively sitting still at the center of the universe. There's no objective actual origin to any objective actual coordinate system in the universe. That's what we're learning here from Galileo. Therefore, every time we go into any situation where we want to care about direction, there's no objective rule about what is positive or what is negative. We get to decide, but we have to decide, and we have to stick with that decision if we want to make distinctions among different directions. So anyway, let's say we decided that to the right is positive and to the left is negative, then accelerations can be negative. But they will be negative whenever velocity numbers are getting lower. I'm going to say this really fast. I'm going to say this really fast because I have 4 minutes left. Accelerations are going to be negative whenever velocities are getting lower. That could either mean that positive velocities are getting decreasingly positive, like I was going that way 30 miles an hour, and then I kept going that way, but 15 miles an hour. So I lost velocity. My velocity numbers went from positive 30 to positive 15. So I have negative acceleration. And everybody be like, yeah, duh, I get it. Negative acceleration means slow down. Fine, got it. But be careful. Also note that if I were going the other way, if I happen to just be traveling south, and we call that negative, then if my numbers went from 15 miles an hour south to 30 miles an hour south, if my numbers went from negative 15 to negative 30, well, then I would be speeding up, but my numbers, my velocity numbers would be going down. It would be a loss in velocity. That too would be considered a negative acceleration. In other words, if you're either slowing down while moving in a positive direction or speeding up while moving in a negative direction, either one is a negative velocity. Just be careful. We'll see that as we do homework. Just be careful about that. Negative acceleration means loss of velocity under either circumstance. I have 3 minutes, but I'm going to very quickly pull. I'm sorry about the chat. I love what I did see in the chat. I mean, both the jokes and the not jokes, but whatever I missed, I do apologize. Maybe I'll look in the thing later, but I want you to see, oh my God. Oh, no, no, no. Wait a minute. Wait, I want to just, I thought sorry, is that, oh my God, hold on. I know I have 2 minutes. I want to keep my promise and help you with this. Where did it? Oh my God, it's so sad. All right, hold on. Wait. How could this be? Oh, yes. Okay. I have 2 minutes. This will take only 2 minutes, but I want. Not 1 minute. Okay, so this is your homework. That's right. Again, I have like 1 minute to do this, but just look at question 1, a very quick review. There's nothing about acceleration there. It's just to remind you and establish like that direction matters. I will literally tell you the answers right now, so you can just make sure that there's not a trick. It's just to get you warmed up and believing in direction. So look, the answers are, draw a diagram, make a decision, what's positive and what's negative. I recommend that you make north positive and south negative, but you can do whatever you want as long as you're consistent with it. But if you make north positive and south negative, then the answers are A, 700 miles, B, negative 700 miles. Like, I know I'm saying this fast, but just so you, okay, I mean, it's not meant to be a trick. Your total distance for a 700-mile trip is 700 miles. But if the trip went from north to south, then the total displacement would be negative 700 miles, right? Then it says, what's the average speed for this journey? Part C, the average speed would be average speed is distance over time. That's 700 miles per 4 hours. You can't see, yes, you can see the 4. 700 divided by 4 is 175 miles per hour. That's the average speed. What's the average velocity? Negative 175 miles per hour. Okay, those are the answers to that. It's not supposed to be a trick. Okay, it's just to remind you that negative signs matter, and they matter even for acceleration. They're going to be a little bit harder once we're dealing with acceleration. To do Question 3, you're literally just going to use the equation that I just wrote on the board for you here. It wrote it in a slightly different way on the sheet, but it's the same equation. You'll be able to figure it out. What I quickly want to say is 429. We're going to end, I promise. But just in question 2, well, question 2 is just trying to say, where it says instantaneous velocity, it's trying to say, notice one thing. On the right-hand side of the definition for acceleration, I said v minus v naught. I didn't put bars over the v's there. I'm saying those are v's that they're not average velocities. They're just velocities at particular moments of time, at particular instants of time. Okay, we can call those instantaneous velocities. It's like not how fast are you going over an interval, but just how fast are you going right now, like the thing the cop pulls you over for. That's called instantaneous velocity. I think you can picture it in your mind. I think you have experience with it. I just want to admit right here now, we don't have an equation for it. Our equation is for average velocity yet. We don't have a procedure. If you're solving for instantaneous velocity, don't plug in to the average velocity equation. Sometimes we don't have one, but this question is suggesting that sometimes you have enough information to just figure it out anyway. And I'll tell you right now, the answer to question 2, you want to think it through. It's not meant to be a trick. Don't use an equation, just use thought. The answer to question 2, to Roman numeral 2, is 80 miles per minute. Okay, I want you to, you'll see that when you see it at home, like, and you'll have to establish why that's the answer. It's not always that easy to calculate instantaneous velocity, but I think it is in that case if you use your common sense. I'm done. Thank you for waiting so long. Sorry about the chat thing, blah, blah, blah. I'll hang out for 2 minutes and answer questions, but then the other class is coming in. But thank you for being so patient. I think you get it. We did get through everything, blah, blah, blah. And thank you again for the whole YouTube craziness, weirdness. I appreciate it very much. Okay. Oh, yes. Oh, sorry, I didn't change the dates. Yeah, 4 and 5 are due not this week, but the next week. I forgot to change them, but 4 and 5 are due Monday and Wednesday of the following, not this coming week, but the next. I will change them. Yes, good point. Have a good day.
Bye, Professor.
Bye. Have a good day. I'm going to stop sharing just so I can see. Have a good day. Yes, bye. Have a good day. Have a very. Oh, Maisha, yes, question.
Yeah,
Yes.
sorry, I just wanted to let you know, I forgot to submit my turn for Monday, so I'm gonna do that right now alongside today's turn, okay?
Great.
Yeah.
Thank you very much. I appreciate it. No problem.
Professor,
Yes.
did you have already graded the homework one? Because I did not receive my grade, or you did not grade it.
Oh, sorry. Oh, no, that might be my, wait, say that.
So
I think,
the homework one, I did not getting the grade. Have you ever graded?
I'm sorry, for some of you, I have not yet. It's my fault. I fell behind. It's not.
It's okay. I could wait. I just make sure I can.
Yeah, no, it's me, not you. I'm sorry.
Oh, it's fine. It's
Okay. All right, sorry. Thank you.